So what determinants really are, they're nothing more than functions on n by n arrays. So if we had an n by n array, then in taking the determinant, what we do is to start with a permutation sigma on our n elements. And we're going to form a product where we're going to take the first element in our product is going to be from the first row, and the column that we're going to choose is the permutation value sigma 1. For the second row, we're going to choose column sigma 2. For the third row, we're going to choose column sigma 3, all the way up to the nth row where we choose sigma sub n. Then once we have our product formed of elements from our picking out one column from each row, then we're going to multiply that one by the sign of the permutation that we used. And then finally, as our last step, we're going to take the sum over all permutation sigma of all of these possible products multiplied by the sign of the permutation. In all, this is a really intense, kind of strange looking formula, or at least I think it's kind of a strange looking formula, and probably not something that you would guess right out of the box. But we'll look for ways to see how this kind of can be computed in a reasonably efficient manner. Okay, so let's suppose that we had a 4x4 array, and let's suppose that we wanted to take the determinant of that. Well, if we were just applying our formula that we just presented, then we're really looking at how many different terms in our group. Well, for our set of permutations on 4 elements, that's really going to have a cardinality of 4 factorial, which is 4 times 3 times 2 times 1, or we're going to have 24 terms in our sum. So if we start off writing our 24 terms, so we just write out 24 copies of our possible products. Now we just label in all of the permutations. So we just label all of our subscripts with all of our possible permutations. And finally, we put in all of our signs for our particular permutations. And voila, we have our determinant on 4x4 elements. And so that was really easy, right? As in most things in mathematics, the formula that we have is really nice for theoretical computation. So if we're using things in proofs, it's great and awesome. Not really so much sometimes when we're just computing things. And so are there slightly better, shorter ways to be able to do that? Yes, there are. Well, if we start with our formula for the determinant, then we can sometimes compress this notation a little bit and write our product in a slightly more compact form, similar to what we do with summation notation, where instead of sigma for sum, we use pi for product of, and with similar indices, we start at 1 and go up to n, of the product ai sigma I. So what we want to do is to group these together based on whether the first term in our product is going to be constant. And so how we can write that, so we break our sum over all possible permutations into a sum where we're holding the first, or the value of sigma 1 constant in each term of our sum. And then we just, to make sure that we get all of our possible permutations, we take the sum over from 1 up to n for our output value of our first element. So now, since our first term is constant in our products, we can take that one out. So j is going to go from 1 up to n. We have our sum over all possible permutations. where our first value is a constant value of j. So we have minus 1 to the sigma, and we have 1j, and then our product I goes from 2 up to n of a I sigma I. So now that with our constant 1 sub j, that doesn't have any dependence on our sigma, so we can actually pull that to the outside. So we have our j going from 1 up to n, a sub 1j, and then we have our sum, sigma in the symmetric group on n elements, with sigma 1 equal to j of minus 1 to the sigma, and then our product, j goes from 2 up to n of a I sigma I. Sorry, that should be an I, not a j. So I goes from 2 up to n of a sub I sigma I. Now what we notice is that one particular part of our expansion, in particular this sum, kind of looks like a determinant on its own. And so let's see if we can turn that into a smaller determinant. So what we really have in our ordering from sigma is really something that looks like this. We have our element j that's out here in front, and then we have sigma 2 less than sigma 3, all the way up to less than sigma n. And so kind of for all intensive purposes, we really have our sigma mapping a set 2, 3, all the way up to n into the set where we have all of our values of 1 up to n except for j. So we've got 1, 2, up to j minus 1. We skip j, we go to j plus 1, and then we go on up to n. Now we can almost think of this as an element, as a permutation on n minus 1 elements. And we can do that in the following way. So if we want a function on n minus 1 elements, so let's say that's going to be tau, and we want it to map into the image n minus 1, 1 up to n minus 1, then kind of quite naturally what we can do on this side is to just say that if I come up with this function, say lambda of k, is just going to be k plus 1. And so we can do a similar thing for our function from 1 up to n missing j up to 1 up to n minus 1. So let's call that one our function mu. And what this one is going to do, if we are less than j, then let's not do anything and return the value that we put in. So nothing changes. So we have sigma, or mu of k is k if k is going to be less than j. And then if k is going to be greater than j, we need to subtract 1 to get those upper elements. So that's going to be k minus 1. And what we end up with then is, quite naturally, just kind of following the arrows, is this function tau looking like, first we apply lambda, and then we apply sigma, and then we apply mu. And so this is the functions that we're going to put to work. So kind of rewriting things a little bit, we still have our sum, j goes from 1 up to n, of our a sub 1 sub j. We'll still keep our sigma as an element of the symmetric group on n elements, where sigma 1 is going to be j. Then we have our sigma 1 to the j, so our sign of our sigma. And what we'll do first is to change our index on our product to be 1 less. So let's go, k goes from 1 up to n minus 1. So really what we're going to take is k is going to be I minus 1. So if I is 2, k is 1. If I is n, k is n minus 1. And so this becomes k plus 1 gives us I. And so with this change of index, we've got a k plus 1 and a sigma of k plus 1. Now what we want to do is to split this product into two pieces. So we say that this is going to be our sum, j goes from 1 to n, a sub 1j, our sum, sigma in our symmetric group on n elements, where sigma 1 is j, minus 1 to the sigma. And now we break our products up into two pieces. So the first piece, we still have our product, k going from 1 up to n minus 1. But now where sigma of k plus 1 is going to be less than j, and so our terms still stay the same, sigma a sub k plus 1, sigma of k plus 1. Then for our second term, we have still k going from 1 up to n minus 1 of sigma of k plus 1, now greater than j. And so what happens here, if this is still our term, stays the same, k plus 1 and sigma of k plus 1. And so basically what we're doing in our matrix is that we're reducing the dimension down by 1. So we are essentially getting rid of the first row, but then we're also getting rid of the jth column. And so what happens when we kind of map this into a new matrix, so an n minus 1 by n minus 1 matrix, where we have b11, b12, all the way up to b1n minus 1, and bn minus 1, 1, all the way up to bn minus 1, n minus 1. Then what happens with this mapping is that we get something that looks like this. Our b sub kl entry is really going to look like, so all of our rows are going to shift up 1, and so this is really going to be a of k plus 1, because things are kind of shifting down. And then for our column, if L happens to be less than J, nothing happens. So it's A sub KL if L is less than J. And then in the case that L is greater than or equal to J, what happens is our columns then get shifted over one to the right. So our rows still increase, but now our column increases as well. And so we can write this in terms of our new kind of embedded submatrix, our B's. So we still have our J going from 1 up to n, A sub 1J. Then we've got our sum, sigma again still in our symmetric group on n elements, with sigma 1 being J. We have our minus 1 to the sigma. And now this first portion of our product is really, since sigma of k plus 1 is less than j, this really is our product. K goes from 1 up to n minus 1, our b sub k and sigma of k plus 1. And likewise, for the second portion, it becomes our product. K goes from 1 up to n minus 1. Again, since sigma of k plus 1 is going to be greater than j, this looks like b sub k, and now our column has to come down by 1, so this looks like sigma of k plus 1 minus 1 for those values. So now we can write our indices in terms of these functions that we've written, our lambdas, our sigmas, and our mu's. And so what that's going to look like, we still have our sum. J goes from 1 up to n, a sub 1j. We still got our sum, sigma in the symmetric group on n elements, where sigma of 1 is going to be j. We've got our minus 1 to the sigma. And now, since sigma of k plus 1 is going to be less than j, nothing was going to happen with our mu. So our k plus 1 looks like our lambda, then we're applying sigma, and then our mu of k plus 1, since we're less than j, nothing happens. And so we can write this as the sum, or the product rather. K goes from 1 up to n minus 1, b of k, and now our functions can look like mu, sigma, and lambda applied to k. And this is going to be for sigma of k plus 1 being greater, less than j. Then we can do the same thing since we have sigma of k plus 1 to be greater than j. Now our mu's end up subtracting 1, but we can still end up with the same form. K goes from 1 up to n minus 1 of sigma of k plus 1 going to be greater than j of b sub k, and we still have mu, sigma, lambda of k. Now, since both of those indices end up looking the same, there's not really a distinction between sigma of k plus 1 being less than j and sigma of k plus 1 being greater than j. So we are able to put those back together as one product. J goes from 1 up to n, a sub 1j. We have our sum, sigma in our symmetric group on n elements, where sigma of 1 is j. We still have our minus 1 to the sigma. Then we are able to put that product back together. Just k goes from 1 up to n minus 1 of b sub k, and then mu, sigma, lambda applied to k. Now for our function tau, if we have, so tau is going to be a function from 1 up to n minus 1 to itself, but if we think of tau really as it is, it's sitting in the symmetric group on n minus 1 elements, but we can really kind of think of tau also being an element of the symmetric group on n elements, where we just kind of make this extra condition that tau of n is just going to be n. And when we do that, kind of what happens, our sign of our permutation, tau, over here with in S sub n minus n, the symmetric group on n minus 1, nothing really changes because our ordering really isn't happening. Our top value is still our top value, so we're not rearranging. He stays on top. The number of transpositions needed to get everything back to our original ordering is exactly the same, whether we see it as a function on n minus 1 elements or whether we see it as a function on n elements. And so in both of those groups, our tau, our sign of tau, is going to be exactly the same. Now the idea is going to be similar to extending our lambdas and mu's onto functions that look like they are really living on n elements rather than n minus 1 elements. And so let's see how we can do that. Again, kind of in our natural way, our function lambda starts off on 1 up to n minus 1, so that's our domain. And then we've got this extra element n, so let's see where we can send that. Well, From our function, we can see that 1 is being sent to 2, 2 is being sent to 3, all the way up to n minus 1 being sent to n, and so the only place left for us to send n is really back to 1. Now, let's do the same thing for lambda. So looking at lambda, what happens there? We've got a domain, again, from lambda going from 1 up to n, but missing j. So we've got 1, 2, up to j minus 1, j plus 1, and then up to n. So what happens here, if we're less than j, we get the same value back. So we've got 1, 2, up to j minus 1. For j plus 1 and bigger, we subtract 1, and so j plus 1 gets sent to j, and n ends up getting sent to n minus 1. So again, there's only really one way that we can extend this, and that is to send j up to n. And so now let's look at what the signs are for each one of these. For lambda, we still have our same basic ordering, except 1 is on top. And so we need to shift 1 a total of n minus 1 spots, so n minus 1 transpositions, to get it back down to the bottom. And so our minus 1 to the lambda ends up looking like just our minus 1 to the n minus 1. Similarly, for mu, what we have is that our ordering is exactly the same up to j, and then it's okay, it's still the same ordering from j up to n minus 1, but this n needs to go back on top. And so how many spaces does it need to go? It needs to go a total of n minus j spaces. And so we had that our value tau was going to be our lambda, sigma, and mu. And so because our signs respect the composition of functions, this means that minus 1 to the tau is really going to be the same as minus 1 to the mu, sigma, lambda. But that ends up being minus 1 to the mu, minus 1 to the sigma, and minus 1 to the lambda, which we just figured out what those values were. Minus 1 to the mu gives us n minus j. Then we've got our minus 1 to the sigma, and our minus 1 to the lambda was just n minus 1. So we end up with values of minus 1 to the sigma and minus 1 to the 2n minus j minus 1. Well, the minus 2n can just go away. So we've got our minus 1 to the sigma times minus 1 to the minus j minus 1. So that we end up with our minus 1 to the sigma really just looking like our minus 1 to the tau times a minus 1 to the j plus 1 when we move that to the other side. And so now it looks kind of like we're doing a re-indexing. So over this set, sigma in the symmetric group on n elements with sigma of 1 being j, we can really switch to a new index, tau, where that tau is going to be to our mu, sigma, lambda. For our tau in the symmetric group on n minus 1 elements. And we know since mu, we can, that one's 1 to 1, lambda is 1 to 1, sigma is 1 to 1. So all of these can be reversed so that basically this kind of change of index we can make also look like that our mu inverse and our tau and our lambda inverse ends up looking like our function sigma. And so if we kind of go through and do this change of index, that this function or this formula looks like. Our sum, j goes from 1 up to n, a sub 1j. Then we've got our sum. We switch to our new set, say tau, in our symmetric group on n minus 1 elements. Then our minus 1 to the sigma becomes minus 1 to the tau times minus 1 to our j plus 1. Then our function, our product, stays exactly the same. K goes from 1 up to n minus 1, b sub k, but then we can write our mu sigma lambda as our tau of k, where we have taken these b's are really just an n by n submatrix where we've gotten rid of the first row and where we've gotten rid of the jth column. Then this expression, if we kind of take out the minus 1 to the j, so we've got an a sub 1j, we kind of take out that minus 1 to the j plus 1, then this expression, our sum, tau over the symmetric group on n minus 1 values, minus 1 to the tau of our product, k goes from 1 up to n minus 1, of b sub k, tau sub k. This one is a determinant on its own, and so we call this the minor of a. So it looks like our determinant, a subdeterminant of this, we call it the minor, and in particular we call it the a sub, since we got rid of the first row and we got rid of the jth column, the minor a sub 1j, or really the determinant. Let's get rid of that and put some more room. The minor is going to be the determinant of that submatrix where we get rid of the first row and the jth column. And so we have our determinant of A looks like our sum, j goes from 1 up to n, of a sub 1j. Then we've got this minus 1 to the j plus 1 times the determinant of our minor, which was our determinant of this a sub 1j submatrix. And we then take this one step further and say this minus 1 to the j is going to be the cofactor of our submatrix, where we're just scaling it by this plus or minus value depending on how we're expanding. Now this is really just a special case of our formula for determinants. There wasn't really anything special about singling out the first entry in our product. We could have singled out any entry, any value in our product, and kind of negotiated everything from there. You get the idea of how the proof might change a little bit if you picked a different element. But kind of in general now, what this gives us is something called the cofactor expansion of the determinant. And what happens when we kind of generalize this to go for any particular value, if we wanted to expand along necessarily any row and any column, how it's going to change is something like this. Our determinant of A ends up being, again, we're doing a sum, j goes from 1 up to n, of a sub, now if we picked any value, say I, j for that, what happens is we have a minus 1 to the I plus j instead of a 1 plus j, and we still have the determinant of the submatrix we get when we get rid of the ith column or the ith row and the jth column. And so with this, we're able to expand and kind of compute the determinant in a more recursive manner. So we don't have to really rely upon the formula. If we were going to compute the determinant, we've got a recursive way of doing that. Actually, there are other ways if we want to get computers or something like that to do it, and we'll discuss those coming up in the next video. But for now, we're running a little long, so let's stop it here and pick this up in the next one.